Well, hello there, this is Ron, and I'm making a video here for my thermodynamics core competency. And this video is about the foundational expectations. In other words, what knowledge should a person bring into thermodynamics? The way this will work is I will show you the knowledge here. I'll maybe add a little bit to it. And then on the second day of class, there's going to be an exam on this knowledge. And people who score with a 4 or better will be done. People who score below a 4 will have the opportunity to keep taking the exam until they achieve the 4. So, that sounds like fun. Yay! So what should a person know when they arrive at thermodynamics? Well, there are 3 major things, and that's 1, to be able to describe certain principles. 2 is to be able to define certain concepts. And 3 is to be able to manipulate units and do unit conversions. I'll show a few examples. So what would I like you to be able to describe? Well, the first is the conservation of energy. It was in Physics 1, it was in Dynamics, it was in Fluid Mechanics, and here it is in thermodynamics as well. Additionally, conservation of mass, also known as the continuity principle. It too is in Physics 1 when I teach it, and it's also in fluid mechanics. And the ideal gas law, that comes to us from chemistry. And Fourier's principle of conduction, as well as Newton's law of cooling. Now, all of these can be found in previous courses. They can also be found on Wikipedia, but I'm expecting that you can do a full describe for all 5 of these. I'm transferring what I have called in the past describe to now something that I'm calling a principle worksheet. But describe is a word definition. It is a sketch, an equation, understanding the units of each of the pieces and parts, and then showing some applications of this to industry. Where is this principle used in the world around us? And then also in connecting to other principles. That's what describe means. Next up, we'll do define. Let me change colors. And define is, by the way, a word definition, a sketch, an equation, and units. And the things that a person should be able to define in this class are mass flow rate, temperature, pressure, density. We use the symbol rho for density. We use the symbol P for pressure, T for temperature. M dot is mass flow rate. Work, W. Power, W with a dot over it. Heat transfer, Q. Rate of heat transfer. Another name for rate of heat transfer is thermal power, Q dot. And a person should be able to know the difference, define the difference between mass and force. All right, well, all of these are taught in physics. They show up in other courses as well, chemistry in particular. The difference between mass and force Mass is a measure of matter, how much matter is there, how many molecules are there in an object, and force is the attraction of that matter to something. And usually I'm thinking about weight. So a pound of mass weighs a pound of force on the Earth, but if you go to the moon and you bring that pound of mass with you, you still have the same amount of matter. You still have a pound of mass of matter, but it will weigh something less. It will weigh about 1/6 of a pound of force. So there's a little bit of a description there. Unit conversions. There are some important unit conversions here. Let me switch colors again. Oops. A square foot is 144 square inches. There are 778 foot-pounds in a BTU. One bar is 100,000 pascals, and 1 pascal is 1 Newton per meter squared. There are 550 foot-pounds per second in 1 horsepower. So those are some of the common ones. What I recommend everybody does is maybe copy the inside front cover of a Thermo book and keep those unit conversions with you. I expect my students to use something called the railroad track method. And I'm going to flip over a page here and demonstrate the use of the railroad track method. So one of the things we'll do is we'll calculate the work done by a pump, and we will see that work is equal to pressure times specific volume. Now, specific volume might be a little new to us. It's the specific volume is the volume of something divided by its mass. And it would have units in English of feet cubed for volume and pounds mass for mass. It is the inverse of density. Density is mass per unit volume. Specific volume is volume per unit mass. So it turns out that specific work is equal to pressure times specific volume. Well, in Thermo, we will typically do specific work in terms of BTUs per pound mass. But an example would be, oh, by the way, this is change in pressure. How much work does a pump do to bring a low pressure from 3 psi to a high pressure on the outlet of the pump of 300 psi? And let's say that the specific volume of the water, let me do that real quick. Is 0.016 feet cubed per pound mass. So I'm going to do the calculation here. The difference in pressure is 297 psi. That's pounds per inch squared. That's the difference in pressure. The specific volume is 0.016 feet cubed per pound mass. And I need to get this into BTUs per pound mass. Now, one of the reasons that I'm doing this foundational exam and this video is because a lot of my students, even as juniors in Thermo, when asked to do this calculation, would just multiply these two things and, I don't know, hope and pray that the answer is in BTUs per pound mass. But it is not. So I need to do unit conversions. Well, just from the other page, I learned that there's 144 inches squared in a foot squared. So now I can cancel the inches squared on the bottom with the inches squared on top, the foot squared on the bottom to get rid of the foot cubed up top. And now I have foot-pound force over pound mass. And also from the other page, 1 BTU is 778 foot-pounds. And that's foot-pounds of force. So canceling again, pounds, force, foot, and we will get an answer, do the math, in BTUs per pound mass. So that's an example of a unit conversion, and I will have an expectation that you can do such type conversions as soon as the foundational exam on the second day of class. So that's an example there. We've done an example here. People might not know this one, so it is the equation for convection. It's quite simple. Rate of heat transfer is equal to a convection coefficient times the area, the surface area of heat transfer, times the hot temperature minus the cold temperature. And so if you're transferring heat, let's say, into water that's flowing through a pipe, so we got a pipe, we got some water flowing through it. The amount of heat that's going to be transferred from the pipe into the water would be a film coefficient, which you learn about that in heat transfer. The area, so it'd be this surface area of the pipe. The hot temperature would be the average temperature of the pipe. And the cold temperature would be the average temperature of the water. So as the water comes in, maybe it comes in at 70 degrees and it goes out at 80 degrees. The whole time heat is being transferred into the water, its average temperature would be 75, and that's what would go here. And maybe the temperature of the pipe is maintained at 200 degrees everywhere, so we would say 200 minus 75, etc. All right, those are the foundational expectations for this class. It's something that should be expected of anybody entering the course. If some of this